Okay, thank you. The title for my talk is Delta Sets for Divisors Supported in 2 Points. This is a joint work with Iwan Dursma. Okay, so, finding the minimum distance for a given code is a very classical problem in coding theory. And for algebraic geometric code, abbreviated as AG codes, the best known bonds come from the order bound. Now, to find the order bound, we use the method called delta sets. Okay, so delta sets requires a lot of computations and a lot of notations, so it's hard to keep track of the notations. So for this talk, I will try to focus more on giving motivations for the delta sets, why and how we came up with the idea of delta sets. Alright, so to start, I'll give some notations. So F is the finite field, and F linear code C of length n is just the linear subspace of F to the n. The Hamming distance of the two vectors x and y are the different coordinates of x and y. And the minimum distance of C is the minimum of the distance of x and y, where x and y differ. So in other words, it's the weight of the minimum weight of the code C, which are non-zero. Okay? And x asterisk y is the coordinate-wise product of x and y. Okay. So x mod f is algebraic curve, absolutely reducible, smooth, projective of genus G over a finite field. And f of x is the function field over that curve. And the Riemann-Roch space is the set of functions, set of rational functions, such that the divisor of f plus a is non-negative. So I usually use half of the audience when I give definition of the Riemann-Roch space. So in the next slide, I'll give a more detailed definition. And the differential module omega of a is the set of differentials where the divisor of the differential is greater or equal to a. Okay? And k is the representative of the canonical divisor, and P1 to Pn is just n distinct rational points on x. And when we say divisor, a divisor is just the formal sum of points. So D is a divisor, which is the formal sum of the n distinct rational points. And when we take G, we want to take G such that the support of G and the support of D is empty. So they have no common points. Okay. So example, what is a divisor of F? A divisor of F means it's a bookkeeping of the zeros and poles. So if we say the divisor of F is 5p minus 3q, it means F has zeros of order 5 at p and poles of order 3 at q. So we keep the zeros and q's. And what is the degree of the divisor? The degree of the divisor is the summation of the coefficients of the point. So in this case, the degree of f will be 5 minus 2, which is 2. 5 minus 3, which is 2. So for Riemann-Roch space, so for instance, if A is 4p minus 2q, I want to find out what the Riemann-Roch space is. So if you look at here, it says the divisor of f plus a is non-negative. A divisor is non-negative when the coefficients of all the points are non-negative. So when a is 4p minus 2q, then f must have at least 2. F has zeros of order at least 2 at q. Right? In order to be positive, it has to have a 0 of order at least 2. And since A is 4p, it may or may not have a pole at p. If it has a pole, it had have order at most 4. Because if it has order minus 5, then this becomes minus p, which is what we don't want. Okay, so this is the Riemann-Roch space. Now we're ready to define the algebraic geometric code. Okay, so we consider two functions, two maps from LG to Fn, and the differential module omega g minus d to Fn. So here, okay, so sorry. So F, so the map alpha L is you take F from the Riemann-Roch space and then you evaluate it at the points P1 and Pn. So this is well defined because G, when we take G such that G has nothing in common with the points P1 and Pn. That means this will never have a pole at G. Okay, so, sorry, this will never have a pole at P1 to Pn. So this is well defined. Okay? And for the alpha sub omega, omega is the weight differential. So we compute the residue at all the points. So this is not that much important because in real we don't actually compute what this is. Okay? So right. So CLDG is the evaluation of the point at F, where F is inside the Riemann-Roch space of G. So sometimes this is called an evaluation code, and this is called the residue code. Now the evaluation code and the residue code are dual to each other. So when we want to compute C omega dg, we don't actually compute this, we just compute the equivalent code, which is CLD k plus d minus g. Right, so for if G has 1 point, this is called a 1-point code. And if G consists with 2 points P and Q, this we will call this a 2-point code. Okay. Now I'm going to define the Hamming distance between two non-empty sets. So the Hamming distance between the two non-empty sets is the shortest distance of the two sets. And the coset is for a proper subcode C prime of C, the minimum distance of the collection of the cosets, which is denoted as d C over C prime, is the shortest distance between the two cosets, where two cosets are different. So you can write it as x minus y is never inside C prime. And in terms of weight, this is the same as saying you find the weight outside of C primes. So x is in C and x is not in C prime. Okay? And you take the minimum. So the coset, this is called the coset bound. And this is the minimum of the weights of x in C, which are not in C prime. So the main theorem is the coset bound theorem, which says that if C and C1 is an extension of affiliated codes with corresponding extension of dual codes, such that the dimension of them are 1. So C, the dual of C is D, and the dual of C1 is D1. Okay? And if you could find vectors from A1 to AW and B1 to BW such that the coordinate-wise product is in D for the sum of ij less than or equal to W, and if I plus j is equal to W plus 1, it goes inside D1 but not in D. Then the distance here, the coset distance here, is going to be greater or equal to W. Right? So if we could find this, so this is for dimension 1. What if it has a higher dimension? We could divide it. Okay, so the D, if this has a bigger dimension than 1, then we could just divide it into smaller ones. So this is the distance of the cosets of C over C prime is the minimum of the distance of C over C double prime and the distance of C double prime mod C prime. And if you want to find the whole distance, the minimum distance of the code, you could always find the minimum of these two. Right? When we say the distance of the coset, this means the smallest weight outside of C prime. And this is the smallest weight inside C prime. So it covers all the whole code. Right? So you could always divide it like this. So I'll try to give an example with a Hermitian curve. A Hermitian curve is a curve which is y to the q plus y equal to x q plus 1. This is an affine notation. We'll assume that it has a point at infinity. Okay, so the number of rational points, Hermitian curve are maximum curve. So it satisfies the Weil bound. So that means it has a lot of rational points. The number of rational points is q to the q plus 1. The genus is q minus 1 divided by 2. And we'll denote the point at infinity as p infinity, and the point, the origin, to be p0. And the canonical divisor is q minus 2h, where h is the intersection divisor of a line. So in other words, this is equivalent to q plus 1 p infinity and q plus 1 p0. Right, so when q equals 4, we have y to the 4 plus y equal to x to the 5 over f16. The number of rational points are 65. I'm going to denote it from p1 to p64, and we have 1 point at infinity. And the genus is 6, the canonical divisor is 10p infinity. Right? So this is more definition. So if f is in the function field, so when we say f is in the function field, you could think of it as you're evaluating f, the domain of f is the curve x. So you're evaluating every point on the curve x. Okay? So f infinity is the pole divisor of f, and f0 the zero divisor of f, and of course the divisor f is going to be f0 minus f infinity. And the Weierstrass group is, so whenever you have a function with pole order n, this is going to be a inside the Weierstrass semigroup. Okay? So in this case, x infinity is 4 p infinity, and y infinity is 5 infinity. So the smallest one is x and y. So the gap numbers, that means you won't have any functions having pole order 1, 2, 3, 6, 7, 11. Right? So these are the gaps. The non-gaps are the Weierstrass semigroup, which is generated by 4 and 5. So you have these numbers here. So there is no functions. These are the smallest functions you could have. So there's no way you could find a pole with order 1, 2, 3. Of course, at 6 you cannot make 6 with these two numbers. All right. So my question is, if G is 17p infinity and D is the sum of the rational points, how can you find the minimum distance of this code? Okay. So we're going to use the coset bound theorem. So my C is going to be what we want to find. This is my C omega D 17p infinity. And C1 is this. And the corresponding dual extension is going to be this here. Okay, so what we need to do is we need to find the vectors A1 through AW and B1 through BW such that when the index are less, the sum of the index are less than W, these go inside here. And if the sum of the index are W plus 1, it has to go inside D1 but not in D. So in terms of codes, you can write it like this. And if this happens, we have the coset distance W. Okay? So let's try to rephrase this. In other words, if there exist functions f1 to fw and g1 to gw such that fi gi, if you multiply these two, it goes into L 17p infinity. That means what? You need to have pole order at most 17. So 16, 15 is okay for I plus j less than w. And now the important thing is here, fi times g sub j is in L 18p infinity minus L 17p infinity. What does this mean? This means that fi gi has a pole only at p infinity here with exact pole order 18. That means fi gi, the pole divisor of fi gi is 18p p infinity. Right? So we need to find functions that has this condition here. If this, we can find this, then we have the coset distance. Okay, so how can we do this? Okay, so this is what we do. So these are the functions. Okay, so these are the functions, and these are the corresponding, the numbers here are corresponding pole orders. So x has pole order 4, y has pole order 5. And the gaps are removed. Okay, so we have these numbers. And then what we want to do is we want to find functions such that, so for instance, if G2 times G7 is, the pole order is 17. So it's inside D, but not in, and if you multiply F8 with G2, the pole order is 18. Okay, so the index here is, if you have 2 plus 7, it goes inside D, and if it's 2 plus 8, it's at 18. So we're trying to find these things, right? So now if it follows from the figure that if I plus j here, if I plus j is less than 9, it goes inside 17p infinity. And if I plus j is 10, then it has pole order exactly 18. So let's see this again. So, right, if I plus j is less than 9, everything is inside less than 18 here. And for instance, G3, if G3 plus F7 is 18, and the other ones are just less than 17. So we want to do this in a systematic way. So we drop the geometry. So we're going to lose the geometry and just think about the numbers. Okay, so this is what we do. So you write down in the first row, we just write down from 0 to 18. And in the second row, we write it down in backwards. And then we cross out the gaps, because the gaps, there is no function that has pole order 1, 2, 3. So we cross these things out. Okay, so the gap number is same as the genus. So genus is 6. There should be 6 gaps. You cross it out and you count the pairs that are left, which are 9 pairs. Right? So you could use an algorithm to do this. So you use the geometry, you use combinatorial methods to find the coset distance. So you apply the same thing for the next one, the next layer, and you get 8. Okay. So you do this until you hit 0. Okay. So the first layer, the first layer here, so this is the whole code, and we want to just find, find the weights for this layer and this layer, and we are doing this here. So this is the coset bound, it's at least greater or equal to 9, and the next coset here bound is at least 8. And then, so the minimum distance has to be 8. So this is how we find the minimum distance. You divide the code into little cosets. You measure the weights in the cosets, and you take the minimum of the weights. So in this case, the minimum distance is 8. All right. So what about 2-point codes then? So the notation, I'll use C omega dg when g is AP infinity plus BP0. I'll just write it as CAB. So in 2-point Hermitian code with Q equals 4, so let's think about 2-point codes. When g is 2p infinity plus p0, what is the minimum distance of this code here? Now the problem is different because when we could go down from either way, so we could go from, we could increase the pole order of p infinity or the pole order of 2p infinity. So you have 2 cosets to consider. Right? And you have to do this for all these codes. So each time you need to make a decision. You go from here, and then you need to decide which way you're going to go. So what we do is we, since this is a finite procedure, so we could do this. So we compute all the weights on these codes, and for each path we have a lower bound, right? We want to find the optimal path. So what we do is we find for each path we get a lower bound for each path. So for each path we get a lower bound. We want to find the best lower bound, you take the maximum. Okay? So you find all the weights for each path you could find, and then you take the maximum of the path, lower bounds. So that would be the minimum distance. Okay. Okay, so the 1 point code is just this line. So the 1 point code is you're just increasing the p infinity, so it corresponds to just this line. But if you consider 2 points, it gets more complicated. Okay. So the Feng-Rao bound, the filtration is determined by the choice of points p. So you have only a line here. Now, Billion bound uses different points for different steps. So this means you could go either 2 ways for each step. So you need to consider a lot of cases. So we want to realize this in we want to interpret this in terms of divisors. So this is what we do. So the minimum distance of CLDG is, so if you look at this, this is G minus C. If G minus D plus A means, this means it has, if this means it has poles, it has zeros at D, right? L G minus D means it has poles at G and it has zeros at D. That means if you evaluated all the points you're going to get zeros, and you don't want that. You want to have non-zeros at A, so you add A. So this is G minus D minus A. So this means you're going to have non-zeros values for A, and you want to find the minimum. So this corresponds to the weight, right? The non-zero points corresponds to the weight of the code, right? And A has to be between 0 and D, and you take the minimum. So this is the minimum distance in terms of divisors. And so you could put C and D minus G, and then it changes into this form. And you could do the same for the residue code. So it has to have poles at A. So this is G minus A, which is different from omega G. And in terms of Riemann-Roch spaces, this is same as K minus G minus K minus G minus A, which is K minus G plus A, not equal to G L K minus G. And also for this, if you put C to be G minus K, this we could write this in terms of this here. Right. And we could do the same for the coset bounds. So this is what we get. So, right. So we just added a P instead of so this is G minus P. So we just added G minus P from the previous, and we get this. And notice we could have a similar type of notations here. So L A minus C is not equal to L A minus C minus P. L A minus C is not equal to L A minus C minus P. So this was the motivation for our delta sets. So if P is not inside D, so P is different from the points D, and if A is between 0 and D, this implies that LA is not equal to LA minus P. Right? So this motivated us to use, come up with the notation gamma PC. So gamma PC is the divisors A such that LA is not equal to LA minus P. This covers this here, this condition, and then the rest, the second condition is given here. So we use gamma PC, and more definitions is that gamma P is, this is something called base point free divisors. So it's a set of divisors such that the LA is not equal to LA minus P. And gamma PC, in terms of the gamma P, is A in gamma P and A minus C in gamma P. Okay, so if you go back, this is the definition. So LA minus C is not equal to LA minus C minus P means A minus C is in gamma P. Okay, and then we want to find the minimum degree of all the A's in gamma PC, and we write this as gamma PC. And then we think about the complement of gamma PC, which is A in gamma P, where A minus E is not in gamma P. Okay, so this is what we're going to study, delta PC. Why are we studying delta PC? Because, so the theorem is, for a rational point not inside PD, we can have the coset bond can be represented in terms of gamma P. Right? So the coset bond, so we need to find, this is C. Right? So we put this as C, so gamma PC. Right? So the coset bonds can be, is greater or equal to gamma P, D minus G, gamma P, G minus K. So we need to be able to find the gamma P of something here. Then we could find the cosets. If we could find the coset distance, we can find the minimum distance. Okay, so why do we study delta PC instead of gamma PC? Because all divisors of sufficiently large degree belongs to gamma PC, while the degree of the divisor of delta PC is bounded. It's bounded by 0 and degree C plus 2G minus 1. Right? So we want to work with something bounded and not infinite. So we work with delta PC instead of gamma PC, although we want to find gamma PC. So for A in delta PC, degree of A is bounded by this number here, degree C plus 2G minus 1. Okay, so we want to find the same in terms of the coset bound in terms of divisors. So how can we find the coset bounds for divisors? This is what we do. So we find the sequence of divisors that are in delta PC such that A sub I plus 1 is greater or equal to A sub I plus P. Then degree of A for every divisor in gamma PC. So we're actually finding the gamma PC. We support this point for AW minus A1. We have degree A greater or equal to W. So so we need to find the longest sequence possible in delta PC to find the coset distance. So why is this true? I'll just give a brief sketch of the proof. So let's just think about A1. So A1 is in delta PC means A1, LA1 minus LA1 minus, and LA minus P is different. Okay? That's the first condition. The second condition is if A1 is in delta PC, that means A1 minus C is in gamma P, meaning LA1 minus C is equal to LA1 minus C minus P. If this is if the Riemann-Roch space is equal, then the differential module is not equal. Okay? There's an if and only if. Right? So for each A1, we could pick functions from here and here. Okay? And that is what we do. This is Fi, and then we pick functions eta sub I. And this corresponds to the vectors that we had before. Okay, so, all right. So another notation is we want to think about the sequences in delta PC, but we want to be more specific. We want to find the sequences B plus IP that looks like this. We cannot find a general sequence, so we're going to limit it to the sequence B plus IP, and we'll use the notation delta P BC. So the corollary is for any choice of divisor B, gamma PC is greater or equal to the number of delta PC, P BC. Right? So if we could find this here, we can find the coset distance. All right. So in finding the coset distance, we use something called discrepancies. Now we want to find the largest sequence possible inside the delta PC. How do we find it? We use something called discrepancies. So here for distinct points P and Q, delta PQ is equal to delta QP. So this is easily seen. If you look at the picture, if A is in delta PQ, that means LA is and LA minus P is different, and LA minus Q, LA minus P, and P minus Q is stay the same. If this is different and this is same, then this has to be different and this has to be the same, right? If this is the different and this is same, this is the same and this is different, so it doesn't make any sense. So if this differ and this is the same, this has to be different and this has to be same, which is the same as delta QP. Right? It's the definition of delta QP. So this is the same. Right? So we denote this as dpq, and the divisors inside of this dpq is called discrepancies. Okay. So a divisor A is called discrepancies for the points P and Q if A is inside this here, dpq. So a theorem. The dimension of the Riemann-Roch space can be calculated using these discrepancies. Right? So you find all the divisors of the form B plus IP plus JQ, which are in dpq, such that I is less than A and J is less than B. So you could compute this using a computer easily. Right? And actually we're interested in 2-point goals, so we could just take B to be 0. Okay? And the notation here, so we want to think about the divisor that has this form, so we give a dBPQ. Right? So how do we know what dPQ is? Right? We need to know what the dPQ is. And so for distinct points, so suppose we know what dPQ is, we could find there's a way to find dPQ, then we could think about two functions, sigma and tau. So we know this has this form. So sigma is here, right? When you have an I, and you have a sigma I, and you have tau j and j. Okay? So there always exists a function sigma and tau, and here sigma tau are mutual inverses and describes permutations of the integers. So it's defined on the integers. That's too many. It's infinite. So how do we do this? So for m minimal, such that mp is equivalent to mq, tau, sigma and tau are determined by modulo m. Right? That means what? dBPQ consists of m distinct divisor classes. So when you know the m values, you know everything because it's modulo m. So you just need to know the m representatives. Okay. So an example using a Hermitian curve is, so y for PQ, for points PQ, MP is equivalent to MQ for MQ plus 1. Because this is a y, the divisor of y is Q plus 1 P0 minus Q plus 1 P infinity. So you have a function which is which is MP minus MQ. So Hermitian curve and Suzuki curves are two transitive. Right? The orthomorphism groups of the curves are two transitive, so you could pick any point. And the m equivalent divisor classes of D0PQ are given as this. Okay, so here H is the intersection divisor of a line, which is Q plus P infinity or Q plus 1 P0. Right? So we know the exact discrepancies. The discrepancies are given like this. And what about Suzuki curves? So I'll give so Suzuki curves. Suzuki curve is, in affine notation, is y to the q plus y equal to x to q0, x to the q plus x, where q0 is 2 to the n, and q is 2 times q0 to the 2. So it's a power, it's an odd power of 2. So when you say Suzuki curve, it's an odd power of 2. And the rational number of rational points is q squared plus 1. It's much more, it has many points. and the genus can be computed, Q0, Q minus 1, and P infinity will be the unique pole of X, and P0 will be the unique zero of both X and Y. And the semigroup, right, the semigroup of Weierstrass non-gaps at P infinity is given here. So this is going to be our M. Okay, so, and the canonical divisor is 2Q0 minus 1H, where H is MP infinity, which is equivalent to MP0. Right. Okay, you could just ignore this here. I forgot to mention what D0, D1, and D2 is. You don't have to know this. This is for proving it. This is a geometry. So you don't have to know this. You just need to know that you could find the M divisors using this here. Okay. So these are the M divisors which we can find. So we know exactly what the discrepancies are for the Hermitian curve. Right, so for example, on a Hermitian curve over F8, the M inequivalent divisor classes are, so M is 13, so there should be 13 of them, which are these here. Okay. Now the theorem here, it looks complicated. Well, it is complicated. So if A is given as Kp plus Lq, and C is IP plus JQ, and then we have these numbers here, right? The important thing is what is DQ and DP. Right? So for MP equivalent to MQ, DP is defined as K plus sigma K in the previous slide, and DQL is L plus tau L. That means since we know the exact discrepancies, we know the exact values of these functions. So this is something we could calculate. So everything is, can be calculated here. Now we want to find the longest sequence inside delta PC. So this is what we have here. So A is not in delta PC, and A minus Q is in delta PC if and only if. So these things are, we can compute this easily using a computer, right? So using this, we could find the coset bounds. So for the Suzuki curve over F32, let C be 55P plus 31Q, and the full grid contains a unique maximal sequence of length 90 when L is equal to negative minus 5. So delta PC contains 90 sequences, a sequence that is has length 90. So in this case, the coset bound will be 90. And you could do this for the whole cosets, right? So you divide the code into small layers, small cosets, and then you find the weights of those cosets and you take the minimum, right? That will be your minimum distance. All right. Okay, thank you.
Are there any questions?